Hello everyone, welcome again. So today's lesson will be on the energy module of Year 11 Chemistry. And in today's lesson we're going to look at explosions, safety and the particle theory. Okay, so we're going to see how explosions and particle theory link up and how we deal with safety and explosions. Okay, so explosions are very typical in Hollywood. Every Hollywood movie has an explosion in it just because it looks cool. So we're going to see how explosions happen and how we can manage them safely. So explosions. So explosions occur when the rapid heat release of combustion is confined to a small area. So when you have combustion, you have lots of heat release, right? But in an explosion, we confine that heat release so that the heat release doesn't escape to the environment. Okay, and it's very rapid. So here you've got like a time lapse or like a frame by frame from a high-speed video of combustion, and it's sort of like an explosion. This is sort of typical of what you'd see in a car engine. So you'd see like a big ball of flame. It'll dilate or get bigger and then fade away, and that causes the pressure to go up very rapidly, and it also causes the temperature to rise very rapidly in your engine. So the high temperatures in this area create high pressures. That's what happens in an explosion. And the rapidly expanding gas is what causes the damage in the explosion. So it's the pressure wave, not the actual flame or heat, that generally causes the damage. Okay. So when the pressure, when the gases expand, they're usually the ones doing the damage, not the actual heat of the flame. Though the heat of the flame also contributes. Usually the first damage is caused by the pressure. Okay, so explosions in the kinetic theory. For explosions to occur, rapid heat release must occur. Okay? This means that the fuel and oxygen must be well mixed and at relatively high temperature. So in your car, the fuel is mixed, in a petrol car, the fuel is mixed very well throughout the air. So the air and fuel are mixed very well together. And then the spark creates a very high temperature location right near the spark. And that causes the flame to ignite. In the case of other explosives, you usually use something to light the explosive. And then it causes a very high temperature region. And that causes the rest of the, sort of like a chain reaction through your explosive. And that causes the heat release to increase, causing an explosion. Okay? If at too low a temperature, the particles will not have sufficient energy, and therefore there will be no reaction. So the temperature has to be correct as well for the reaction to happen, and that's the local temperature, not the sort of ambient temperature. So it'd be the temperature in here, in this part of the system, not outside. Okay. So in an explosion, in an explosive, the temperatures caused by the fuse or the blasting cap can get very, very high. So then maybe just in this top region, the temperature will be really, really high, which will be enough to start the reaction, okay? But the ambient temperature may be like 0 degrees Celsius, but the explosion will still happen, okay? So we're talking about the local temperature inside the system, not the temperature of the ambient air, okay? For explosions to occur, the fuel must be in gaseous state or finely ground solids, okay? For explosions, we need gaseous molecules. And then you might be wondering, well, why does, like in all the movies, the C4 or, dynamite and things, they all look like they're just these solid lumps, okay? But basically, those solid lumps get stuck to something, and then they stick another explosive onto them. That other explosive ignites and then heats up the area near it, causing that section to reach a very high temperature, which causes it to become gaseous. So if this was the explosive, it may be solid, but and this part may be the sort of auxiliary explosive. They'll light this part first, and then it will cause this section here to get very, very hot, and then that will cause this section to explode, and then that will sort of filter downwards. And this all happens very, very quickly, so you don't even notice that this is actually occurring. Now the reason they have to be gaseous or finely ground solid is to ensure a fast enough reaction rate to achieve the high temperature and high pressure rise of an explosion. Okay, so we want to achieve the very high temperature and high pressure of an explosion, so we need the particles to be very mobile so that they can collide rapidly with one another at the right energy. Okay, so explosions and fine particles. Now, explosions do not need gaseous reactants. This is something that catches a lot of people off guard. Explosions don't just occur when there's gases. Okay, so in this picture, this is actually a coal explosion. You can see that that's an explosion. You can see it, but it's caused by coal powder, not by, petrol or something like that. Or hydrogen. It's actually caused by coal. Now, if a solid is ground finely enough, the large surface area can cause explosions. Okay. Sawmill dust and ground coal present a large explosion risk. Okay, so another example of explosions is sawmill dust. So when a company, logs down a forest, and they take it to the sawmill, and that sawmill cuts up the tree, the dust from that sawmill can actually, if there's enough energy or something causes them to ignite, can actually cause an explosion because it's so finely ground. Okay. So safety and particulate fuels. As mentioned already, there are certain requirements for explosions to exist. Okay, so without meeting these requirements, you don't get an explosion. So the 5 requirements are a fuel. So if I'm just standing in air, I'm not going to explode randomly because there's no fuel. I'm not a fuel. The air is not a fuel. So that's 1. You need heat, something to start the reaction. Obviously, you need oxygen, okay, because there's fire involved. So you need oxygen. Suspension, so you need the fuel to be suspended throughout the oxidant, or at least be mobile enough to sort of to move around. So it needs to be suspended. And it needs to be confined. So if I have all this coal dust, out in a field somewhere, and I try to light it on fire, and there's a gust of wind blows by, nothing's going to happen because there's too much mobility. The coal will just get carried away, and my little lighter will just, be on. Okay, so you need to confine it. That's why they try to ventilate things as much as possible to get things moving from inside out into the environment where it won't cause any damage. Okay, so confinement is a big one for explosions. Okay. By removing any one of these, explosions are no longer possible. So if you remove confinement, then you can't have an explosion. If you remove suspension, so that everything's on the floor or something, then you can't have an explosion. Same with heat, fuel, or oxygen. Okay. So for particulate fuels, explosions can be avoided by ensuring a suitable number of air changes within a space. So what that means is that if you're in a factory working with coal or working with sawmill dust, if you move the air from inside to outside, so have proper ventilation and filtering, you can prevent explosions because obviously you're taking the dust and particles out of the air. Tighter restriction of machinery could stop particulates from escaping into the air. This is more important for coal because in the coal industry, you grind up the coal to burn. So if you have better control over your grinding process, you may be able to stop the coal dust from escaping your grinding process. This one's a little bit harder in a sawmill because your saw kind of generates dust and you kind of let that go into the atmosphere. But again, you probably could control it if you had enough time or engineering practice. You probably could control that as well. And ensuring that the machines are kept cool, so lower than the ignition temperature of the fuel, then you could prevent accidental ignition of these fuels. Okay, so there's another way of preventing explosions. Okay, so that concludes today's lesson on explosions and safety. We looked at how explosions occur, what they are, and particularly we looked at solid fuel explosions and the potential risks that they pose. Okay, So not many people think of coal dust and sawmill dust as explosive, but they can be in certain situations. So hopefully you've learned something about safety, and we'll move on to the question segment now, and hopefully you can pick up more tips or information about this sort of esoteric topic. So number 1, or question 11 in this case, explain why finely ground solids can cause explosions. Well, since the particles are so small, the surface area exposed to the air is extremely high. So when you grind up coal, you get a lot of surface area, and that's good for combustion in terms of when you put it into a boiler or something to produce electricity. That's good, but in the air where there's workers who are working and don't want to be exploded, that's not so good. So when there's lots of surface area, you get fast reaction rate between the solid fuel and the surrounding air. And this rapid reaction causes large increases in temperature and pressure, resulting in an explosion. Okay? So it's just because there's a lot of surface area available that you get these big explosions when you deal with finely ground solids. Okay? It's been said that an empty coal warehouse may be more of an explosive risk than a full one. Explain how this could be possible. So if I've mined out my coal and then I've stored my warehouse full of these lumps of coal, and then I decided to move them, that empty warehouse could actually be more dangerous than the full one. Okay? So when the warehouse is emptied, fine particles of coal may be released into the air, just by moving them. You agitate the dust, and then the coal dust goes into the atmosphere, or goes into the air. Okay. When the warehouse was full, there was not enough space or available air for an explosion to happen. Okay, so even if the coal dust was in the air, there would be less air space available, and also the coal would have burned very slowly anyway, taking up even more of that air. However, once the actual coal is removed, the dust remains, now with larger access to air and more space to sort of mix more homogeneously. Thus, an explosion is more likely in an empty warehouse than a full one. Okay? So an explosion isn't likely when you have lots of lumps of coal, because the coal won't explode. It'll just burn very slowly, which is bad, but it's not an explosion. Whereas when it's emptied, the fine dust of coal that's floating around may actually explode because it's mixed very well with the air, and has a lot of space to maneuver, and it will be still confined within the warehouse. So explosions are more likely in an empty warehouse. Explain why, with the exception of finely ground solids, fuels need to be in gaseous form to explode. Well, explosions require a fast reaction rate. Therefore, a large proportion of the fuel molecules must have the correct activation energy. So remember that the distribution of energy looks sort of like this, where this is the activation energy. So very few particles actually have the correct energy. Okay? Whereas if we increase the temperature or the mobility, it sort of looks like this now. So a lot more particles have the correct energy, right? So that's why we need gaseous form. Gaseous form means that more particles will likely have the correct energy. So in a gas, it's far more likely that the fuel molecules have the correct energy than if it was in a solid or liquid form. Okay, so that's why they have to be in gaseous form. Okay. Dynamite, probably you've seen it in your cartoons. Wile E. Coyote tries to use this a lot. So dynamite is a powerful explosive used in the mining industry. It's used to sort of break rocks open. So when placed in a fire, dynamite doesn't explode. Okay? So if I put my piece of dynamite into a bonfire, it's not going to blow up. Sounds dangerous, but it's not. It's fine. But however, when the fuse is lit, so when you actually light the fuse on fire, dynamite creates a powerful explosion. Now, can we explain this? So dynamite is designed to be stable and difficult to initiate. So dynamite is designed not to explode. Again, that sounds really counterintuitive because dynamite isn't explosive, but it's designed to be stable and not explode. So why do we do that? Well, obviously it's done because you don't want the dynamite unexpectedly exploding in, say, the high temperatures of a mine, or if you drop it. So you don't want an explosive where if you're walking through a mine or something and you drop it, it's going to blow up inside the mine. You don't want that. So that's why they purposely make dynamite very stable. And also the temperatures in a mine can get quite high. There's lots of machinery, lots of people working. So you don't want your stick of dynamite just exploding randomly because the temperature suddenly got a little bit higher. So it's designed not to do that. However, the fuse is actually used to ignite another explosive, which provides the appropriate activation energy to initiate the explosion of dynamite. So your dynamite has actually another explosive connected to one end, which is called a blasting cap. And so when you light the fuse actually ignites the blasting cap, which then ignites the dynamite. So you've got actually another explosive causing the main explosive, the dynamite, to explode. So when placed in a fire, the chemicals in the dynamite do not receive the energy fast enough for an explosion to occur. So when you put it in the fire, the heat of the fire takes a fairly long time to get into the dynamite. So it won't actually cause it to explode because the heat going into the dynamite is not rapid enough. Okay, the transfer of heat isn't rapid. The only way to do it is with the blasting cap, so you can actually cause it to explode that way. Okay. Though, I'm just going to caveat this whole thing by saying it's probably not the safest idea to try and putting dynamite into a fire. It has been done before, but I wouldn't suggest it because dynamite is still explosive. So don't play around with it too much. Okay. Nitroglycerin, which is this, is used as an explosive in engineering projects. This chemical undergoes the following fast, strongly exothermic reaction. So explain the usefulness of this chemical as an explosive. So you can see here that nitroglycerin goes to form nitrogen gas, water, CO2 and oxygen. So it's quite an amazing little fuel. It even sort of oxidates itself, which is kind of cool. You don't need any oxygen to make it explode, which is cool. It's very interesting. So this reaction produces a large volume of gas. All products are gases, and many moles of each gas are produced. So you can see 4 moles of gas, of nitroglycerin, gives you 16, 28, 29 moles of gases out. So that's more than 7 times, 7 times the volume of gas that you put in. Okay. And large amounts of heat. So you get big volumes of gas and large amounts of heat. This heat will make the gases expand rapidly, causing an explosion. So that's the usefulness of this chemical as an explosive. It can create a very large explosion because it can produce lots of volumes of gas and lots of heat, which can cause the gas to pressurize. Okay. So that concludes today's lesson on explosions and safety and particle theory. So we looked at how explosions happen and how explosions happen in solid state, and we also looked at what kind of safety measures we can do to make explosions with finely ground solids less of a problem. So hopefully you've learned something about explosions and also explosions for solid fuels, and hopefully you'll be able to see the potential risks of using solid fuels when there's explosion risks occurring. So that concludes this series on classifying combustion. So I look forward to seeing you at our next lesson.